So, okay, we'll start now. So, I just start by introducing myself. So, I'm Sathasivam from ISATVM. I'm a PMR fellow. So, and this is my email ID if you have it, wants to contact me. So, so today what we are trying to do is we try to solve some problems related to the subgroups and cyclic groups. So, also the center and centralizers. And if there is a time, then we will also try the homomorphisms. So let's start with the problems related to subgroups. So the first problem says the following. Suppose if you have a two subgroup H and K, then what can you say about H intersection K? So in general, is it a subgroup or not? So what we can say easily is H intersection K is actually subgroup, but union one has to see whether it's a subgroup or not. Okay. So the first problem says, suppose if H and K are subgroup, then prove that H intersection K is subgroup. So in order to prove that, what are the things you want to prove? You want to prove all the four properties, right? So let's start with one by one. So let's start with the closure. So here what we want to prove is, suppose H comma K belongs to H intersection. Immediately say. Suppose G comma G1 belongs to H intersection K. So we want to prove that G1, this also belongs to H intersection K, right? So this is what we want to prove. So why is that true? Let's start with the observing. See, G belongs to H intersection K means what? It means G belongs to H and G belongs to K, right? So it belongs to both of them. And similarly, G1 also belongs to both of them. So in particular, what we know, because it's two elements are belong in the intersection, what we know is, so this is the claim that we want to prove. So what we know is G belongs to H and G belongs to K. So similarly, G1 also belongs to H and G1 is also belongs to K. Okay. So let's do the first one. Since G belongs to H and G1 also belongs to H, what we can say is the product belongs to H, right? Because H is a subgroup. And similarly, what we can say here, these two things implies that G1 belongs to, sorry, G1, this belongs to K. And these two things together, this implies this. So what we have is the product Gg1, it belongs to both H and K, and hence so H intersection K. Okay. So the closure is done. So what about the associative? Associative follows easily, right? So why the associativity is true? Associativity is true because see we start both of this are the subgroup of G, right? So in G there is associative. So that will holds for any subset also. So H intersection K is also the associative holds. Okay. So as long as if it is a hold in a bigger set, it always holds in the smaller set. So it follows from the associativity of G. Okay, now what about the identity? So let's say one be the identity of G. Okay. So what we know is this one belongs to H. Why? Because H is a subgroup. What is the reason? Reason is since H is a subgroup. So H is a subgroup means the identity must belongs to H. And 1 also belongs to K because K is a subgroup. Thus 1 belongs to the intersection. Okay, so this is also easy. Now what about the inverse? Here also we do the same thing. Suppose G belongs to uh, H intersection K. First what you start is G belongs to H. So G inverse also belongs to H. Now this same G belongs to K also. So G inverse belongs to K also. So if you combine these two things, what you get is G inverse belongs to H as well as G inverse belongs to K. Okay. So we have checked all the 4 property. Thus G inverse H is a group. Sorry, thus H intersection K is a group. I mean, of course, it's enough to actually check uh, the closure and the inverse. Okay, so other things are true anyway. So as long as you do, I mean, if you want to check some set is a subgroup, it's enough to check the closure and the inverse. But here we have done everything, but it is enough to just do the closure and inverse. Okay, so here is a remark. I will just write. Suppose let's say I is a indexing set. So by indexing set, I mean it's just any subset, any set. I'm just going to use this to index my collection of set. Then if you look at AI, comma I in I, so be probably I change the color here. This is not a good color. Suppose these are all subgroups of G. So what I'm telling here is, so I have collection of subgroups AI, okay, and all of these AIs are a subgroup of G. So this I runs over some index set. Then in general we can prove the intersection I in I, AI is a subgroup. So here the I need not to be countable or anything. I can be any subset. Sorry, I can be any set. So still you can prove. The proof goes exactly like this. So exactly like all the 4 property you are going to prove. But here you cannot write like that. So you just have to write it generally. Okay. Instead of H and K, you write the just AI. That's all. Here replace this by AI. And then you get the proof. Okay. So let's move on to the next problem. So now we have seen the intersection of a subgroup is a subgroup, right? So the next question comes is what about the union? So is the union a subgroup? So suppose if I have a 2 subgroup H and K, is the H union K is a subgroup? Okay. If it is not a subgroup, can you come up with a counterexample? So that is the next question that we want to see. So maybe you can try for I think few minutes, then I will tell the answer. So you try to think about the groups that you already know, some easy groups you take, and then try to take the union and see if it is a subgroup. So in general, union of two subgroups need not to be subgroup. So here is a example that I will give here. For example, you take the group G to be Z2 cross Z2. Okay. So you take the product of two cyclic group Z2 cross Z2. So now what you do is you consider this a subgroup. The subgroup generated by, let's say, A, or maybe I will take H and K. So let's take H to be 0, 0 and 1, 0. Okay. And take the K to be 0, 0 and 0, 1. Okay. So you can clearly see these two are the subgroups of G. Okay, that you can prove it. It is easy to see here. So I will write it here. Check H and K are subgroups. So if you add any of this element, it will still be there, right? If you add 0 with this, it will be still the same element. If you add this element twice, you will get this. And the inverse of this element is the same element. This is the identity. So this is basically isomorphic to Z2. And if you know what is isomorphism means. Okay. Now we have two subgroups. Let's take the union. If you take the union of H and K, what you get is this set, right? You get 1, 0 as well as you get 0, 1. But if you take these two elements, 1, 0, and you add it with 0, 1, so you get 1, 1. So, but this element is not in the H union K. So it's not closed under, binary operation. Okay. So that tells you in general, union of two subgroups need not to be a subgroup. One can also give much complicated example, but even the easy example says that you cannot in general do it. So the question is, okay, if you cannot say in general, then in which time that union of two subgroup is a subgroup? So when will be union of two subgroup is a subgroup? So that is the next result says that. Suppose if H and K are two subgroup of G, the union is a subgroup if and only if either H is contained in K or K is contained in H. Okay. So that is what we want to prove. See, if you look here, this direction is actually easy, right? Let's prove this direction easily. Okay, so the statement says the following, right? Either this has to happen or this has to happen. So let's do each of them separately. Suppose if K belongs to H, then what happens? Okay. So here I'm just writing, I'm going to prove this direction. So then what happens is, what is K union H? This is H, right? And H is a subgroup. So subgroup of G, let's say. Okay. So if you take the union is a subgroup. Okay. And the similarly, one can do the case. H is contained in K. Okay, just change the variable. You will get the same proof. Okay, so here you'll get H and K, and here you'll get K. Okay. So this direction is easy. Now let's try to prove the other direction. Here you are assuming that H union K is a subgroup, and you want to say that either H is contained in K or K is contained in H, right? So here what we assume is H intersection K, sorry, H union K is a subgroup. So what is the claim? Claim is either H is contained in K or K is contained in H. Okay, so when you have a statement like this, okay, the statement says either this is true or this is true, right? When you have a statement like R statement, and if you want to prove some R statement is true, the usual strategy is assume one of that is false, and we will prove the other one is true. Okay, so that is the usual strategy to prove. Of course, one can prove it many ways, but we will prove this way. What we do is let's assume that H is so basically H is not contained in K. Okay, we will prove K is contained in H. See why this is equivalent to proving this? Because suppose if it is true, okay, say what if you look here, what are the possibility? Either H is contained in K or H is not contained in K, right? If suppose H is contained in K, then this statement is true. So thus we can assume that H is not contained in K, and in that case this has to be true, right? So basically here is a statement and here is a statement. Let's say call this statement P and this is Q. If this is true, whatever the value here it is, the R statement is always true, right? So sorry, R statement is always true. As long as one of them is true, the R statement is always true. So what we are going to do is we assume that first statement is false, and then we will show the if that was the case, here we will show the second statement is true, and hence your statement will become true. So we want a true in the last column. So for that, what we are going to prove is, so we prove that the Q is true. So basically, we assume this is false and prove this is true. Okay. So how do you prove that? So here, what you have to prove is this is a subgroup of this, right? So basically, if you take any element here, that has to belongs to here. That is what you want to prove. So let's start with the element. Let's K belongs to K, and I want to say that K is contained in H, right? So how do you say? So it's not direct that K is always contained in H. So you have to come up with a way to make it happen. Okay. So but let's try to see what we know here. What we know is the union is a subgroup. Okay. So if you take the K here, and let's say you put any H here. So I will just write the idea here. It's an intuition I write here. Then probably I write the proof rigorously. See, suppose if you take any H belongs to H, okay, then what happens? This both of them, both K and H, this both belongs to H union K, right? So for any H, this both this K and H, this belongs to H union K, and this is a subgroup, right? So what we have is this KH, sorry, K dot H, this belongs to H union K. Okay. So what is K dot H belongs to H union K means it belongs to either H or it belongs to K. Okay, and now we have to use the property. Suppose if I say it does not belongs to one of that, then I can exploit it. I will tell here how. Probably right here. So let's say H belongs to H. Okay. Then what happens? Then what you have is HK. This belongs to H union K. Why? Because this is a subgroup. So HK belongs to H or HK belongs to K. This is what we have, right? So now what we can do is let's consider both of this case separately. What you actually wants to prove is this K belongs to H. Okay, so this is what you want to prove. Suppose if this is true, let's say you assume this is true, then see what happens. You have HK belongs to H. So that implies what? That implies HK is some H1. Okay. So then you can multiply by the inverse. You can see that K equal to H inverse H. H inverse H1. This belongs to H. And then you are done here. Okay. But the problem here is it can not necessarily always belongs to here. It can belongs to here also, right? So in that case, you cannot directly choose any H. If you randomly choose a H, it can belongs to here also. The HK can belongs to K also. So there is a very small trick you have to see. So I will write the trick. So what you do is you choose a K, because here you observe that H is not a subgroup of K, right? So there is an element of H which is not in the K. I'm going to use this particular hypothesis, and this tells me there exists a H in H such that H is not in K. Why that is true? This is true because the H is not a subgroup of K. Okay. So basically, it's not a subset. So there is one which is a outside K. Okay, and we choose this particular H here. Okay, so once you choose this particular H here, so this is, let's say this is case 1. Okay, so what is the case 2? So the case 2 is the HK belongs to this particular K, right? So the case 2 is HK belongs to K. Okay, suppose HK belongs to K, then what happens? HK is equal to K1 for some K1. Okay. Now you multiply by K inverse. So what you get is H equal to K1 K inverse. Okay. So here you see this belongs to K, this belongs to K, so this belongs to K. Okay. But if you observe here, we choose this H in such a way, this H does not belongs to K. Okay. So if suppose this case happened, that implies this happens. But this is a contradiction, right? So a contradiction. So this case cannot happen. Okay. Thus HK belongs to K is not possible. See, the contradiction happens because see, here there is two possibility, but the contradiction happens when I assume that this is the possibility. So if this is not the possibility, then I only end up with this possibility, that I can always say that K belongs to H and we are done. Okay, so we want to prove, remember, we want to prove that K belongs to H. Okay, so that is what we want, and we start with the element K and we proved that belongs to H. So we are done. Okay. So union is a subgroup if and only for one of them, one either H is contained in K or K is contained in H, then it's a subgroup. Otherwise, it is not a subgroup. Okay, so let's move on to a different problem here. So this problem says the following. So you have a G here, which is a GLN. It's a okay. This group is called a general linear group, right here. So it's called. So these are basically matrices. So what is this general linear group? Probably I think Sir has defined it, but I will just define it once again. So if you don't know what is a field, just assume that by F I mean real numbers. Okay, probably I'll just replace it by real numbers. So this is nothing but n cross n matrix. So set of all A such that what is the A? A is n cross n matrix. And I also need that determinant of A, and this is not equal to 0. Okay. So if you know a little bit of linear algebra, then you can see why this is important. These are all the vector spaces isomorphisms. But anyway, let's not go into those. But you can see it as a matrices. So these matrices are n cross n matrices, but the determinant is 0. So basically invertible n cross n matrices. So determinant not equal to 0. This is same as telling invertible. Okay. So since it is invertible, it has the inverse, right? So this is a set, and what is the operation? Operation is matrix multiplication. Okay. So star you put as matrix multiplication. Okay. So under this operation, this GLN-R is a group under the matrix multiplication. So that is what we have. So G is a GLN-F, but here you just assume it is R. If you don't know what is a field, just assume it's R. And SLNF, this is a set of all matrices in GLN such that the determinant is exactly 1. So here the determinant is non-zero, but SLN we are calling is a special linear group. So this is called a special linear group. So I will write here. So this is special linear group. Okay, and so what we can observe is this SLN R. This is a subgroup of GLN of R. So that is the question. So that is what we are going to prove. Okay, so how to prove it? This I will assume. I think Sir has done in the class. So this I will assume. This is a group under multiplication. I think this is a known. I think it has been done. So let's prove the SLN. It's a subgroup. So in order to prove the subgroup, it is enough to prove only the closure and the inverse, right? So we'll just do the both of them. Okay, so that is one of the test here. If you don't see why it is the case, here you come here, here you can see the associativity, it follows from the bigger set. So for example, when you prove here, you can observe that if the associativity true in the bigger set, let's say in G, then it is also true in the small set. And similarly, the identity also. So okay, identity, or how you can get the identity? Maybe I'll write here. Okay, so associativity will be fine. Why if the associativity? Okay, maybe will not write here. So suppose you have a set H here, which is let's say it's a subset, not a subgroup, but a subset. Okay, of G, which is closed under, let's say, binary operation and inversion. So the inverse also belongs to there. So then what we can say is then H is a subgroup. So this is subgroup of G. Okay, why it is the case? What are the other property you want to prove? The associativity and the identity, right? So associativity holds because it holds in the bigger group. So associativity you don't have to worry. What about the inverse? For inverse, what you do is you take the identity is another thing you want to prove. So you take another H here. Okay, you also have to assume that H is not equal to 0. Okay. So let's take the H belongs to H. Then consider H. Okay, H inverse. See, because of the inversion property, I know that H inverse also belongs to H. And then this product, because of the closure, this belongs to H. But if you look at what is H inverse, that is identity. So this belongs to H. Okay. So it is enough to.
Excuse me, sir.
Yeah.
Here, when we're saying it is not equal to 0, we mean it's not a null set, right? It is a
Yeah,
file.
yeah, exactly.
Yeah, okay. Okay.
Yeah, yeah.
Thank you.
Okay, I want to write the empty set here rather than 0. Sorry. Yeah. Okay, thank you. I have to write this is not an empty set, not a 0. Yeah. Because if I say 0, 0 is actually element. So yeah, I mean empty set. So the identity will belongs to H. So in fact, all you have to check is just the closed under binary operation and inverse. So let's check for SLN. So recall that SLN is a n cross n matrices. So SLN is a n cross n matrices with the determinant is equal to 1. Okay. N cross n invertible matrices with the determinant equal to 1. Okay. So let's check on the. So what we want to check? You want to check closure. So let A comma B belongs to SLN. Okay. Then what we know about A and B? We know that the determinant of A, this is equal to 1. This is equal to determinant of B, right? This is what we know. So what we claim is AB belongs to SLNF. This is what we are claiming. Okay. So basically what we need to prove is determinant of AB. If you take, we need to prove this is equal to 1. So this is what we need to prove. Maybe I'll write it properly. So I will write, we will show. So once I show this determinant of AB equal to 1, then I'm done, right? But the determinant, we know the formula. Determinant of AB is nothing but determinant of A, determinant of B. Okay. So in fact, later we will go, when you go for homomorphism, I think it was done in the lecture that determinant is actually homomorphism. Okay. So what is determinant of A? This is 1. Determinant of B is also 1. So 1.1 is 1. So this is 1. So the closure is done now. Let's look at the inverse. Inverse also goes the same way. So let's say we take A belongs to SLN. Okay. So how do you find the determinant of A inverse? So I want to find the determinant of A inverse, right? So this is the claim. So we know the determinant of A is 1. We are claiming the determinant of A inverse is also 1. Okay, so see, there is a property you can directly assume that what is the, if you know the property of determinant, you can directly do. But let's not worry about any property. All we need is the determinant is a homomorphism. So this is all we need, and then we will go with it. Okay, so what we know is A inverse this identity, right? Now apply determinant on both sides. Determinant A inverse is equal to determinant of identity. Determinant of identity is nothing but 1. Okay, and determinant of A inverse, this is the homomorphism. Okay. Sorry, this kind of splits here. So we have a determinant of A, determinant of A inverse. Sorry for using the word homomorphism. We'll come back later. So it kind of splits here, and this is equal to 1. Okay. So from here we can observe that determinant of A inverse equal to 1 by determinant of A. So this, but you can write here, provided determinant of A is not equal to 0. Okay, if it is not equal to 0, then we can write. And in such a case, only A inverse exists, right? So, okay. Anyway, in our case, what happens is determinant of A is 1. So determinant of A inverse is also 1. Okay, since determinant of A is equal to 1, what you have is 1 dot determinant of A inverse. So from here I'm writing. Of course, one can write from here also. But okay, here provided. Okay. But kind of this, yeah, okay, that is fine. So 1 times determinant of A you take here. So this is equal to 1. This is determinant of A equal to 1. Sorry, A inverse. Okay. So that proves the, so we have shown that the inverse is also inside SL. Okay, so these are some groups for which you can talk about the subgroup, etc. So this GLN is actually, probably will tell some remark, like which are the things that we are going to do later. But I'll just give something like we are going to do, and that's what I will say. So there is one important thing about this. So maybe I'll tell now so that when you see the theorem, you can appreciate it. So let G be any finite group. Okay. So what we can do is the following. Then then we can see G as a subgroup of GLN. Let's say any field here, but I'll just put R. Doesn't matter, you can put any field you want. Okay. For the large enough n, actually. So for some n. So basically what I'm telling is you take any finite group, that is a subgroup here. In fact, one can also say that any finite group G, so you have studied a symmetry group, right? So what we can say is, suppose if order of G is equal to n, then we can say that G is a subgroup of Sn. Okay, so this we can say, and this theorem is called Cayley theorem. So later we will do here, but this Sn one can embed into GLN. So basically we have this kind of subgroup relation. Any group G belongs to this Sn, and this Sn will belongs to this GLN, where n is basically the order of the group G. Okay. So in that sense, GLN is like the more general, like any group you want to study, it's enough to study GLN. But it also tells that how complicated the subgroup structure of GLN are. So if you want to study all the subgroup of GLN, it's same as studying all the subgroup of so it's same as studying all the finite groups. So and there is so many groups. So it's in some sense it's impossible to study all the subgroups of GLN. But some other groups you can study. For example, Dihetal, quaternion, and abelian groups, we can study all the subgroups. But this GLN is one such group. It's there are so many subgroups inside. Anyway, so now you can see why the matrix theory is somewhat important. Well, although here we may not use much matrix theory, although these are all matrices, we may not use much matrix theory, but you can see every group is basically a matrix. So any element of a group, you can see it as a matrix. Okay, by that I mean if you take Z2, you can see Z2 as a 1, right? 1, 0. One can ask how can I see it as a matrix? Okay, so but that one has to say how to see it as a matrix. I'm not going to say it here, but there's something called isomorphism, and you can see there's an isomorphic copy of G inside that. This G need not be inside that, but there's an isomorphic copy of G inside that. Okay. So when I say subgroup, it's not exactly this. For example, if you look at the Z2 is 0, 1, right? This 0 will not be in, it's not a matrix. This is a number, right? If the n is, let's say, larger, in this case, the order has to be 2, right? So this is a GL2. These are all 2 cross 2 matrix. So this 0 is not inside a 2 cross 2 matrix. So that is not what I'm trying to say. But there is some copy of this inside it. And there is something called isomorphism, and up to isomorphism, this is a subgroup. Not exactly the same group, but yeah, up to isomorphism. Okay, so I may not need this page, so I will delete it. Okay, let's move on to this one. So this one, I think this has done in the last tutorial also. So we have tutorial both on Monday and on Tuesday. Okay, so both on the same time, 6 to 8 p.m. So you can choose whichever one you want to attend. More or less, we do different problems. But this is one problem that I picked from whatever he is doing, because it seems it's a very important subgroup. The subgroup is a very important subgroup. So I thought, okay, why not we do it also? Okay. So the question is the following. Suppose, let's say H is a subgroup of G. Okay. And G is any element of G. So then the claim is you're defining a subgroup here, GH G inverse, which is the set of all G small h G inverse, where the small h belongs to H. So you take all the H and then you write a GH G inverse. So the claim is this is a subgroup of G. Okay, and this subgroup is called probably right here. It's called the conjugate of H by G. Okay. So this word conjugate, you can see the things like this one. This is actually very important later on. Because see, you can observe that what probably when you go to the next maybe here the center etc. Here I will explain why it is important. But if I don't explain, please recall me. I will tell you why it is important. But right now, let's just prove this is a subgroup. Okay, again, what we want to prove? We just need to prove the closure and the inverse, right? So let's start with the closure. Maybe I will use the same color here. So what you want to prove? You want to say, let's start with the G and G1 belongs to G. Sorry, maybe I will write different notation. Yeah. H and H1 belongs to H. So what we want to prove is GH G inverse times G1 H1 sorry GH1 G inverse. This belongs to H, right? So basically, I take two elements here inside the this set. Okay, and I want to say this product is inside H. Okay, when I write like this is what I mean. Okay. So now what you can do is you can change the brackets, right? So GH G inverse G. Sorry, yeah, H1 G inverse. Okay, this is same as this. So this is my claim, but this element is same as this element. So okay, here see I'm using associativity to bring this to this. Okay, so for example, see this as a one element. So basically you have to use associative. There is multiple step you have to write in between to get here. You have to change the brackets. So but associative also tells that however you put the bracket, it doesn't matter. So I directly write it here. But there are multiple steps one has to write if you want to write all of them. Okay. But if you want to see how to do that, in the last tutorial we have done it. So you can check in that one. So, but I don't know which time we have done it. I mean, like which time in the video that we have done it, that I don't remember now. But we have done it in the last time, so you can check how to change the brackets if you really wants to see. But associative tells you whichever the way you put the bracket. So even if you put like this, it doesn't matter. Okay. So as long as you have associative, all the ordering of the bracket is kind of the same. That one can prove in general. But it's tedious to prove it, and so we'll just assume it. Let's not prove it. Okay. So here you observe that this I can cancel out. Okay. So what remains is basically GH H1 G inverse, right? So this is this belongs to H. Why this belongs to H? Because you see H and H1 belongs to H. This implies what? This implies H1 belongs to H, right? So this particular one belongs to GH G inverse. Because this one belongs to H, and hence this entire thing belongs to GH G inverse. Okay, so closure is done. Basically, we are cancelling it out. That's all. Now let's do the associative. So not associative. Inverse I want to do. Okay, so let's say I take GH G inverse belongs to GH G inverse. Okay. Now what is the inverse of this? So here from here, in this calculation, probably you try to see what is the H1 I need to put to get identity. You put any H1, this is what I'm getting, but I want to make this as identity, right? So what should the H1 I have to choose? So basically the inverse, so I'll write here GH G inverse, it's inverse, it's nothing but G H inverse G inverse. That's the obvious candidate, right? So let's multiply it and prove that it's identity. That's all. So let's say GH G inverse. Then you multiply that way. So how do you prove some element is so how do you prove this is the inverse of this element? So you just have to multiply and say it is equal to 1, right? And that is what we are going to do. Let's say GH inverse G inverse. Let's multiply. But this is nothing but GH G inverse G H inverse G inverse. And this I can cancel out. And this became G H inverse G inverse. This also I can cancel out. I think it is clear from now, right? It became G inverse, and this is equal to 1. Okay, so that tells you this is the inverse of this element. You can multiply in the pre-multiply also. And do the same thing, you will get exactly the same thing. Okay, so this is the inverse. So what we have is we have both the closure and the inverse, and hence this is a subgroup. Okay, so this is a subgroup now. Okay, so let's go on the probably after the next problem. Maybe I'll tell you why this kind of I may not tell why this subgroup is important, but probably will tell why this kind of operation is important. So you're taking one element and then put the one element here and the inverse here, right? Probably you'll try to see that. So this was the one of the exercise in the book. Maybe I will small. I'll take this thing somewhere here. Make it a little bigger here for you to see. We will just make it bigger. Okay, so the problems. Okay, now we will move on to the next topic, which is the centralizer, center, and what is the conjugation. So these are the next topic that we are going to do. Okay, so these are the exercises mentioned in the book. Maybe I'll erase this. So the first exercise says the following. Suppose if G is a abelian group, then center of G is equal to G. Okay. So what is the center of G? Center of G is the set of all elements which commutes with G, right? So what is the center of G? Center of G is what? This is a set of all G in G such that GH is equal to HG for all H in G. Okay. So basically this is a set of all G which commutes with every element of G. Okay. When it is equal, when you have this, like you multiply in this way or multiply the other way, if it is same, then we say this two elements commutes. And if G commutes with every element, then we say G is in the center. So what here is the statement is, suppose if G is abelian, then the center is actually G. Okay, let's prove that. So, okay, maybe I will write one by one here. Probably will call this one 6A. Call this one 6B, 6C, and 6D. So we can do each one of them. Okay, probably we'll spend some time in that because this centralizer, these are important concepts. So, okay, maybe I'll tell why it is important later. Okay, so what I want to say is, if my group is abelian, then the center is equal to this. Okay. So we will doing 6A now. So suppose let's say G is a abelian group. So what does abelian means? If you take two elements G and H in G, then what we know is GH equal to HG. So this is the definition of being abelian, right? So if this is true, then what is the center of G? So one thing is obvious, right? Because the center of G is always a subgroup of G. Why? Because you are always collecting an element from G with some extra property you're putting. So the center of G is always a subgroup of G. That is clear. It's clear. I mean, ideally, one should not write clear, but because this is basically you're collecting element from G. So that means any element here is an element of G to begin with. So center of G is a subgroup of G. So what we want to prove in order to say the equality, so we will prove those. We will prove the other equality. The G is contained in the center of G. So how do you prove anything like containment? So okay, by this I mean subgroup, but by subgroup also means it contains, right? So if I say it is contained, then it is fine. So how do you do? Let's start with the G in G, and we will prove that this G belongs to center. Okay. Then what we know? We know that GH is equal to HG for all H, right? So this is for all G comma H. So the statement says take any G and any H. This is true. Here I am fixing a G, but then I can choose any H, right? Then because your group is abelian, then for any H in H, what we know is GH equal to HG. So that is same as telling that G is in the center, because that is the property we need, and we have that. Thus, G belongs to center of G. Okay. So actually, there is nothing to prove here. It's just whatever comes here, you are just redefining. I mean, we are just writing it down there. That's it. So there are so many statements here, but we did nothing. So don't confused by the too many statements that I am writing here. Okay, now let's prove this one. Okay, so what is the centralizer? Centralizer of A, you take a small a belongs to G. So what is the centralizer of A? It is a set of all elements in G which kind of commutes with A. Okay, so what is the difference between center and centralizer? Center has to commute with every element of G, right? But the centralizer is only commutes with that particular element. Okay, so that is called the centralizer of G. So now the first one is centralizer is a subgroup of G. Let's prove it. So C G of A, right? Let's notice. Okay, he writes only C of A. So basically, when there are more groups, for example, you have something like H is a subgroup of G, and suppose if A is an element of H, then when you want to talk about centralizer, you always talk about centralizer H of A or the centralizer G of A. So you want to say from which set you are. So when you take the centralizer, you're taking this G, right? This G from some group, right? That group you usually write here. Provided when things become complicated and there are two groups and you want to study about the centralizers, then you used to always specify from which group you take the elements to form the centralizer. Okay. But in this case, there is only one group, so there is nothing to worry. So he doesn't put any subscript. Okay, so I will also follow the same thing. But if you want, you can put the subscript to specify which group this G is coming from. Okay. Okay, so what does the centralizer mean? So it is a set of all elements that commutes with A, right? It's a set of all G in G, such a GA equal to AG. Okay, so let me take a two element, G comma H belongs to CA, belongs to centralizer of A. So what we want to prove? You want to prove the closure into the inverse, right? Let's prove one by one. So we are trying to prove that it is a subgroup. So we want to prove the closure and the inverse. Okay, so let's prove the closure first. Okay, so let me write GH. We want to claim that GH belongs to the center, right? So centralizer, right? So that means what? GHA, this has to be equal to AGH, right? So this is the claim. Okay. So now how you do that? You just change the brackets and then you do. So let's start with the GHA. Apply the associativity, make a GHA. Okay, but this is nothing but GAH. Why? Here you're using the fact that it commutes. Okay, these elements commute. So G and H belongs to centralizer. That means G and H, the order you can change it. Okay, so this order I changed it here. Now I change the bracket, use the associative again to change the brackets. So now I commute it again. G, H. Now again use the associativity. A, G, H. Okay. So we got it. That is what we want to prove. So basically just associativity and use the property, you will get it. Okay, so closure is done. Okay, see, associativity I can use here because associativity is anyway true in any set as long as, associativity is true in the G, right? So I can use the associativity of G. These operations are the operation of G, so associativity holds. Okay, because here we didn't prove associativity, and one can say you didn't prove associativity, you're just using it because it's the associativity in G that I'm using. Because the operation in the subset comes from the operation of the G. Okay, so what is the other property you want to prove to make it a subgroup? You want to prove the inverse, right? So inverse is a little bit a tricky one. Let's see if we can able to do that. So what we know is, let's say G belongs to centralizer of A. So what is this? This tells you this is same as telling GA equal to AG. So the claim is the G inverse also belongs to the centralizer, right? So what we want to prove is, we will show G inverse A. This is equal to A G inverse. Okay, how do you do that? This is maybe a little bit tricky. So maybe I will give you a few minutes to think. Maybe I will give you 1 minute to think at least. It's not hard, okay? It's not hard. Just to do a small trick, it will come. But if you do it for the first time, then you may need some time to think. So maybe just take 30 seconds or 1 minute, then probably I'll tell the answer. But it's kind of good idea to try. So if you have any idea, you can let me know. And if you guys want some break, like maybe 5 minutes break or something? If you want, you let me know, then probably you can have it. Otherwise, I will continue. See, what we have is, we have a GA equal to AG, right? What I want to prove is a G inverse. So from here, I have to somehow get here. That is the idea. So what you do is, see, all you know is this, so start with that. Okay, so GA equal to AG. This I know. Okay. What you do is just multiply both sides with, let's say, G. not G. Let's multiply both sides with the G inverse. Okay. So this is the same as telling, because somehow we have to go to G inverse, right? So let's just blindly multiply both sides with G inverse. So G inverse AG is equal to, sorry, G inverse GA equal to G inverse AG. Okay. So here I can cancel out these two things. So what I get is A equal to G inverse AG. So if you see, it is still no better here, but already you can see why this kind of elements come into picture, right? So the conjugate, these elements here that we were discussing about the conjugation. So you can see that these elements come into picture. So it is important because it comes usually it keep on coming. So then one will see, oh, okay, what happens with this? So I don't see there's any other reason why it is important other than that it just keep on appearing. So one is curious to study that. That is all that is happening. Okay, so now here, if you look here, what you have to use is that G belongs to centralizer, right? So let's use that. Okay, so we have A here. This is equal to, now here I can use centralizer. Now I can cancel it out. See, I'm skipping the bracket, but if you want to be rigorous, you always have to write the bracket. But associativity, once you have, doesn't matter which order you put the bracket. So I'm kind of skipping it. So what does this tells you? This is not what I want, right? No, this is not what I want. Yeah, if you cancel it out, see, if you cancel it out, what it tells you is just A equal to A, right? But that is not what you want. Okay, so no, just give me 1 minute. Canceling out here. I don't know if I even multiplying it. Sorry for the thing. I just got a little bit confused. It's not anything hard. I just got confused. Anyway, from here, let's say we directly do here from here. Okay, we have this, right? So from here, we directly use the property. So anyway, we start with the commutativity of G, right? So this basically, we already use this property. So G belongs to the centralizer of A. We already used this to start with. So I was wondering that because next step the answer will come. So I was wondering where I actually used it. I start with that. Okay. So we have this. Now what you see is multiply both sides by G inverse. Okay. Put the G inverse on both sides. Okay. So if you multiply both sides by G inverse, what you can observe is this. You can cancel it out, and whatever remains is A G inverse is G inverse A. Okay. So that is what you want to prove. Well, the other way, this equality doesn't matter which way you want, right? It's a kind of symmetric. Okay, so we will show that. We already done. So that means the inverse. So once you show that, what does it means? The inverse belongs to the centralizer. Okay, so that is done. So since we have done both the closure and inverse, that tells you the centralizer is a subgroup. The centralizer G of A is a subgroup. Okay. Okay, so let's move on to the next one. Okay, yeah, there is so many here, I think. Probably I may skip one of them. All of them are just you have to keep doing the same thing. So maybe let's do this one. So this one is okay. Maybe I will skip this one because this one is clearly obvious. Why? What I want to say is center is contained in centralizer of A, right? What a center means, the elements in the center commutes with every element of G. In particular, it commutes with A also, right? So if you take element of G, it commutes with every element. In particular, it commutes with A. Thus, it belongs to the centralizer of A. That's all. But I will just leave it as exercise. I mean, I have already said the answer, but probably you try to write it down. So sometimes a good idea to write a simple thing, so you at least get the idea how to write it. Okay, so let's try this one. This is the G is abelian, then the centralizer of A is actually G. See, we have done a similar question here. G is abelian, then the center of G is A. Here we are saying centralizer is also A. So even though, okay, so here also we don't have to do anything. Use this and this, then you are done, right? So let's use the 6A and the 6C. See, one can always write with the elements, okay? But sometimes, and most of the times I will say, when you can able to use the previous theorems that we have done, that is kind of the thing that we may need for later. So let's not do this one by element, but rather we just use whatever we have already done and conclude it. Okay. So remember this: if a group is abelian, then the center is equal to G, and the center is contained in the centralizer. Remember these two facts, and we will do the last one. Okay, 6D. Let's do that. So what is the claim? We claim that centralizer of A is equal to G if G is abelian. Okay, so now what I have is the following. So we have that the centralizer of A, this is contained in center, right? And of course, center is contained in G. Okay, so this much we have. Now, no, sorry, I read it other way around. Center of G is contained in centralizer of G. So center of G is contained in the centralizer. This we have by 6C. This is by 6C. Okay. Now by 6A, what I know, if your group is abelian, then center is G. This is by 6A and this is by 6C. So what does that tells you? Let's forget this one. Okay. What does that tells you? It tells you G is a subgroup of C of A. Okay. And this is the subgroup of G. So that means G equal to centralizer of A. Okay. So you don't have to go with the elements. You can directly write telling that G is equal to centralizer. We will write it properly. See, centralizer of A. Okay, so that is what we have here. Okay, maybe I'll just give a remark. Okay, here is something, right? Probably we'll do this one also. Okay, so this problem says what? Okay, I will write what is the centralizer. Recall what is the centralizer. Centralizer of A is a set of all G belongs to G, such that GA equal to AG, right? So here what the problem says is I can write the centralizer as this set. This set is the set of all G in G, such that GA G inverse is equal to A. So basically this statement is equivalent to this statement is what it's telling. But that is obvious, right? Because GA equal to AG, this implies what? Multiply like in the right, multiply in the like post multiply this element by G inverse. Okay. So do this one. Then what happens is this cancel out. That is what we have. Okay. So let me write it here. G inverse equal to G inverse. But then this cancel out. So this is equal to GA. So this is if and only if G inverse. So also if and only if equal to A. Okay. So these two statements are equal, and hence these two subgroups are equal. Any element here which satisfies this property also satisfies this property. So any element you take here, this will belongs to here. Okay. Suppose you take a element here, it satisfies this property, and hence it satisfies this property. So this belongs to here. Okay, so that is how you want to write the proof. But there's nothing to write here, so I didn't write it. Okay, let me tell you what is the, I mean, so this elements here, so I will put a remark here. See, this conjugation is there, right? GAG inverse. It kind of captures whether G commutes with A or not. So when, if you have a group in which every element commutes, then those groups are actually nice groups. So because those groups you can easily study and you know how the groups looks like also. Okay, but when two element does not commute, that creates so many problems. And in this particular element helps you to figure out whether G commutes or not. Okay, why? If suppose G commutes, then what you have, GH inverse is equal to A, right? If this happens, then G commutes. Otherwise, G does not commute. Okay, so that is why we always work with these elements. And sometimes what people do is they just modify this a little bit. So if suppose G and A commutes, if you modify a little bit, what you can write is GA, G inverse, A inverse equal to identity. You can write here. Okay, and this people give a symbol. It's called GA, and they call it a commutator. So this is just a notation. This bracket is just a notation for this element, and they called it a commutator. Commutator GA. So it's called commutator GA. So this commutator captures how far your group is being abelian. Suppose if your group is abelian, all this commutator is equal to 1. Okay. Suppose if your group is not abelian, then these are the abstraction for your group to being abelian. Okay. So later, I don't know if you study in this course, but this is one of the important one. So all of them kind of comes with the conjugation. Hopefully in this course you will study something called class equations. Okay. So I'll just say what is that. Maybe you Okay, I think I got yeah, internet was gone. Sorry about that. Okay, I will share the screen again. Okay, so remember this formula. GCD of A in a set n, order of A power m is basically n by GCD. So let's do one by one here. So order of 3 is what? It is 20 by, see, in this case, what is the generator? What is, okay, probably I'll write, maybe we'll just change it here, everything. I'll write A cube square. Okay, so what is the order? Order is basically 20 by the GCD, right? So it is 20 by GCD of 3 comma 20. But 3 and 20 does not have any common factor. So this order is basically 20. So okay, what about this one? The second one order is 10 by GCD of 2 comma 10, right? GCD of 2 comma 10 is 2. So we have 10 by 2, which is equal to 5. Okay. So in this case, what? It is 10 by, see, I'll skip the GCD, I'll just write the bracket only. 7 comma 21. You see, means I just, it means GCD, but I'm not writing in the front. So GCD of 7 and 21 is again 7. So this is 10 by 7, which is equal to, sorry, not 10 by 7, 21 by 7. So that is again, that is equal to 3. Okay. So what about this one? So this is also again, I think is 11 by 7 comma 11, right? So 7 and 11 is a kind of co-prime. So GCD is actually 1. There is no common divisor, right? So GCD is 1. So this is equal to 11 by 1, which is 11. Okay. So if you want to compute the order, so this is the formula that you use to compute the order. So when you work with this cyclic groups, there is a theorem which you know that it says that given any order dividing n, there is always a unique subgroup of that order, right? And that subgroup is also cyclic. So that theorem is very useful, and then you always try to remember that theorem. And that kind of tells you the entire structure of the cyclic group. So now let's move on to another problem here. So what I was trying to say is, if you have cyclic group, all the subgroup structure is kind of known because the theorem says you how all the subgroups are there. Anyway, I didn't write the theorem. I'm just telling there is a theorem which you might know from the lecture. Okay, so let's do this one. It says we will start with the z by 15z, and you want to find all the generators of z. Okay. So when you say something is generator, if I say, let's say x power I is a generator, then what has to, suppose this is generated by x, let's say. Okay. X power I is generator means what? If you look at x power I, this subgroup order has to be 15, right? If this subgroup order has to be 15, then this is also generator. So in other words, what you have to say is, uh, yeah, so the order is actually 15. If the order is also 15, then you can see that this is also a generator. So that means what? That means what you have to do is, you do this, but the GCD has to be 1. So if A power M is a generator, then the order has to be n. That means the GCD has to be 1. Okay. So that means x power I is a generator. if and only if I comma n equal to 1. Okay. Here I will write it clearly, generator of Zn. Okay. Now let's write all the generator here. So what are all the generators here? I want to write what are, so basically the problem is same as telling what are the I here, which is a kind of co-prime to 1. When I write here again, it means GCD. Okay. So what are the I here such that I comma n is actually 1. But in this case, n is 15. So let's write every number and see, right? Okay, let's write every number. We have 1, we have 0, 1, 2, 3. Not 15. No, 15. No. Because x power 15 is anyway. Yeah, that is not co-prime anyway. Okay, let's write everything. Is 0 co-prime to 15? No, right? Here in our case, n is 15. 0 co-prime to 15. What does this mean? It means there is no common divisor, right? GCD is 1 means there is no common divisor. GCD is basically the greatest common divisor. If it is 1, that means other than 1, there is no common divisor. But if you look at 0 and 15, 15 divides 0, 15 divides 15. So there is a common factor. So this is not correct. Okay. 1 and 15, there is only one common divisor, which is 1. 2 and 15 you took, that is also there's only one common divisor. 3, there is a common divisor. If you look at the 3 and 15, there's a common divisor, which is 3. So this is not. This is correct. This is not. This is also not correct. Sorry. Yeah. So this one, why? 5 is a common factor, right? 5 and 15, 5 is a common factor. If you look at 6 and 15, 3 is a common factor. So the GCD is 3. So 7 is there, 8 is there. This is not, this is not, this is there. Okay, so these are the I. So the generators, if you look, the generators are basically x square, x power 4, x power 7, x power 7, x power 8, x power 13, and x power 14. Okay. So these are the generators. Okay. Just give me 1 minute. I will tell you one more result. Probably. So how do you find the, so this how many generators we have? 1, 2, 3, 4, 5, 6, 7, right? So we have 7 generators. So if suppose I give a n to you, okay, so let's say we work with the Zn, and suppose I give you this particular n. Now the question is how many generators are there?
Sir, one little doubt, sir.
Yeah.
Sir, Z suffix 15 is same as Z slash 15 Z. Both are same, sir.
Z slash this one, right? You are telling this one.
Yes, sir.
This is same as Z less 15Z. That
Yes,
is
sir.
the question, right? Yeah, there is something called isomorphism. Up to isomorphism, they are the same. So basically, the group structure is the same. But probably when you study the isomorphism, you can see how it is. Is the isomorphism is thought?
Sir, my doubt is this is a quotient group or is it?
See, Zn is just defined in this way. You take this and then whatever comes, then you will just put it inside. That is how the Zn is defined. Of course, you have a quotient group, which is a Z mod 15Z. So this is also there. But this group, how do you say? This group is isomorphic to Z15. Okay, so these are same groups actually. These are same, but if you look directly see in let's say if you look at Z mod 15 set, let's say if you look at one element, let's say one, how the one looks like, one looks
Sir,
like
what are
one.
the elements of Z slash 15 Z and Z15?
See,
What is the difference, sir?
elements of Z slash 15 Z looks like this, right? It looks like X plus 15 Z.
Oh,
Okay, element looks like that. Here the elements looks like just X square, etc. Okay, so the element looks different, but it's just the change of the name. Other than the change of name, it's the same thing. But probably I will tell you here because you
okay.
asked. I will tell something. So let's consider two groups. Let's say you take the I here. Okay, you take I and 1, where the I is the complex number. Okay, so this is actually a group under multiplication. Let me call this as A. This is a group under multiplication. So why? You see, this I is I square is equal to 1, right? Sorry, I square is equal to minus 1, not 1. Let me take 1 and minus 1. There's nothing here. Okay, so this is the group under multiplication. But if you look at this one, 0 into 1, okay, and let's say this is Z2. Okay, so this is a group under addition. It is a group, right? So how do you do? 2 times
Sir,
1 is
Z2,
actually
Z2 are clear, sir. But
no.
Z slash.
I understand. I will tell you what is isomorphism here. Then that group is isomorphic to Z here, Z2. Okay.
Oh,
So I was just trying to say what is the notion of isomorphism, but I don't want to go into Z mod 15Z. If you know Z mod 15Z, I can directly say. So anyway, I'll just tell here. You let me know if it is clear. I mean, it looks like I'm going in different direction, but I will come back. Don't worry.
okay. Okay.
So if you look here, what happens is this two groups looks different, right? But on the other hand, it's actually the group structure is same. So what happens is there is one element which is kind of the identity here, and the other element has the property. If you take this element, star it with the same element, you will get the identity, right? Here also you take this element, add this with the other element, you will get identity. Okay, this is a modular addition. Okay, so basically, even though this groups looks different, if suppose I change this name to some other name, this is the same group. Basically, this is the same group, but the names are different. So let's say my name is, let's say here. So for example, you take this dot. Okay, let's say I called it blue. If somebody, let's say, called it purple. Okay, however you call it, the dot is just a dot, right? The color is just the same. Just because you call it purple does not change this color, right? Similarly, what happens is this group, if you look at the underlying structure, those are same. But somebody called it 1 while I called it as 0. You call this as minus 1 and I called it as 1. But the operation you put the operation as the star and I put the operation as plus. But the group structure is the same. Okay. And somehow we want to capture, although this groups looks different, but the structure, underlying structure is the same. And that was captured by the notion of isomorphism. Since we have done what is a homomorphism, I will tell you what is isomorphism. Isomorphism is a phi, a map from G to H. This is called isomorphism if phi is homomorphism and phi is bijective. Okay, so if these two properties are satisfied, then this phi is called isomorphism. Okay, so basically this phi is basically what it tells you is you take an element here and you just relabel into some other name. So here you have a name here, call it X, but I am giving you different name, and I am going to tell you once I change the name, the group is just the same. Okay, instead of seeing it as a 1, if I see it as a 0, then this group is kind of the same. So that is what this isomorphism captures. So basically these two groups are different. By looking you may see it is different, but these are not different, but just a relabeling of each other. It's just changing the symbols, but the structure is the same. So similarly, what you can show is this group Z, let's say Z15. This you can show it is isomorphic to Z mod 15Z. Although if you look here, elements, if you look here, this elements looks like what? Let's say one element I take here. Maybe I'll take this element 1 plus 15Z. Okay. If you look at this element is basically a set, right? In Z mod 15Z, this element is a set which will be 1 plus, sorry, 1 comma 16, etc. Comma 31, I think 46. This element is a set, but in this group, the 15, let's say you take the 1 here. This 1 is basically just a 1. It's just a one symbol, but here there is a set here. So in that sense, if you directly look, these groups are not the same group because this element is not the same element here. So set theoretically, they are not the same set. But if you look at the structure of the group, what happens here? You go 15 times, you will come back to identity. Here also the same thing. Go 15 times, you come back to identity. So the structure is same. So these two are isomorphic. They are not like as a set, they are not same, but these two are isomorphic. But since we are doing group theory, we care about, we just care about the structure. We don't care about how we differently relabeling it. See, you are calling it 1-0, then I can also call it as let's say something like that, right? Let's say I can say this is my set. These two symbols here I can write, and I can say this. I can write something like that, right? I can put two different symbols. And this is also another group of order too. But you see, at the end of the day, if you look, this group and this group are the same. I mean, just I changed the name. So in that sense, that these groups are same. On the notion of isomorphism, they are same. And when group theorists talk about equality, we talk in the context of isomorphism. When we say two groups are equal, we say they are isomorphic. For us, equality is same as isomorphism. Because whatever the name you put, because one can always put 1,000 symbols and then one can say there are 1,000 group, but I don't want 1,000 group, but I just want to see what is the structure. The structure, if you look, there is only one structure, and that is just the same. But these are all different labeling. But later when people use it, you just people interchange these two symbols. Some people write the Z mod 15Z, sometimes the same time you will also write Z15, because up to isomorphism they are the same. Is that clear?
Yes, sir. Clear, sir.
Okay, good.
Thank you.
Yes. For example, one can also say something like this. For example, you have this Z, right? One can say this is a subgroup of Z cross Z. Okay, but if you look here, element here looks like 0, 1. But the element here, sorry, let's say A, B. But the element here looks like just A. But how do you see as a subgroup? But I see element here as a element in Z here, let's say A. I see it as a element something like this. And in that way, I can see this is a isomorphic to a subgroup inside this. Okay, and such a way people talks about it is helpful because you just want to study the structure. The labeling doesn't matter. So isomorphism just to capture how two groups are relabeled. That's all. Okay, let's move on to other one. Here I was trying to say something. Yeah. So if you look at Zn and you want to find how many generators, so Zn have. So this is called, this is denoted by the number phi of n. Okay. And this is a Euler function. I think I'll just write Euler function. Okay. So for a prime p, let's say p power n, the function is given by p power n minus p power n minus 1. And if you have two numbers a and b, a b, such that let's say you have A and B are co-prime. Okay, so basically the GCD is 1. Then phi of AB is same as phi of A times phi of B. So this function is multiplicative. So if you have any number with these two properties, you can write this function for any number. Okay, maybe we will just write this for one particular number. Let's say 15 we will write. Okay, so what is 15? Phi of 15, right? Let's say we write 15 is what? Phi of 3 times 5, which is phi of 3, phi of 5. And how do you write phi of 3? Because this is 3 power 1, right? So that is 3 power 1 minus 3 power 0 times here we have to write 5 power 1 minus 5 power 0. So I think this is 2 times 4, which is 8. Okay, let's check. We have 8 generator. 1, 2, 3, 4, 5, 6, 7. Oh, I think I missed one. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I kind of missed one. Which is the one I missed? Yeah, 11 I missed here. Okay. So the number of generator is given by this, and you can directly write this. Okay, so this just I'm just recalling this, and you can check and verify that you got all the generator by finding the number of generators. Okay, so that is just a recalling. Let's move on to the next question here. Okay, so this is a kind of interesting one. See, what we know is Z is a cyclic, right? So we know this one, Z is cyclic. So the question is Q cyclic? And is R cyclic, is C cyclic? So these are all directly one can ask. So, okay, so our idea is to prove whether they are cyclic or not. So the first thing at least says that Q is not cyclic. So let's prove it. Probably this is maybe the only interesting problem in this entire tutorial. I mean, I will not say, but yeah, but at least this is the most interesting. That at least that much I can say. Okay. So what does the mean by saying a group is cyclic? Say I say G is cyclic if and only if G is generated by a single element, right? So if you take a power 0, which is actually 1, so that means this G has to looks like 0, which is basically a power 0, which is identity. Maybe I call it identity here. And a power 1, a square. And here you go minus 1 also. So G has to looks like this. Then I say it is a cyclic group. Okay. So the question is Q is a cyclic group? Okay. So when Q with addition actually, okay, when you write Q is a group under addition. It is not a group under multiplication because 0 does not have inverse. So when I write Q, I mean Q plus. Okay. So I mean, I one basically just write Q because it is understood from the context that either if you look at multiplication or addition is the only one which makes it as a group. So okay. So suppose if Q is cyclic, that means what? Q is generated by a single element, right? So basically it's generated by some element like A comma B. And all the other element has to looks like n times A by B such that n belongs to integers. Okay. So here it's a multiplicative notation. Here I'm writing additive notation. So here it's n time. I mean n times when I write n times A, I mean sorry, n times AB, I mean A by B plus A by B plus etc. N times you just do this. This is n times. N times you are adding it. Okay, that's what I'm writing like this. This is not multiplication. This is I'm not multiplying n and AB. In fact, that is true. You can multiply it, but here I just means add it n times. But that is same as multiplying in the Q. But that is anyway. That's a different story. Let's not worry about that. Okay. So moreover, what we can assume is we can assume that they are in the reduced form. This AB, let's say we can assume that it is in reduced form. We can assume that A and B is coprime. Okay. If not, if it is not coprime, just divide by the common factor and make it as coprime. Okay. So this is just this is not anything serious because we can always make it coprime. Okay. Now what you can do is you try to see what happens. Suppose if I write B as a, see, I can use the fundamental theorem of, see, B belongs to the integer, right? So I can use the fundamental theorem of arithmetic to get the B is written as some, let's say, plus or minus 1, sorry, plus or minus, let's say P1 power alpha 1, P2 power alpha 2, etc., Pn power alpha. Okay, so I can write B as a product of finitely many primes. Okay, it's very important that I can write it as a product of finitely many primes. And the primes that appear here is unique also. Okay, by fundamental theorem. Some people call this a prime factorization theorem. The set P1 to Pn and also the exponent, but they are unique. Okay, so this is what we have. Now let's look at what happens with n times a. Okay, so suppose if I add a plus abb plus abb, what will I get? What you get is nothing but you get 2a by b, right? And you see, you are always writing, in some sense you are writing as a, you know, lowest denominator. Okay, so whenever you get something like that, always cancel it out, write it as a lowest denominator. So because it doesn't matter if you have 2 by 4, this is same as 1 by 2. So you can always assume this is 1 by 2. Okay. So why we are writing in the lowest denominator is because if I can write, there are many way you can write denote this 1 by 2, right? In some sense, I want a unique representation. Usually in a rational number, you won't get a unique representation. You can write this as p by q, but then you can put any n up and down. It's the same representation, right? I mean, denotes the same number. So there is no uniqueness there. If you want uniqueness, you always impose that there is no common factor. Once you impose there is no common factor, then the representation is unique. That's why I always wants to impose this is coprime to get a unique representation. Okay. Okay. So what you can do is you can cancel it out all that you want. If you want to cancel, if there's a common factor, you can cancel out, etc. But what you can observe is the denominator. If you look at denominator, so whatever the denominator you come, let's, and okay, probably I'll write maybe some statement I will write. So the denominator, if you look, the denominator is basically b, right? Or even if you cancel it out, what you get in the denominator, maybe let's cancel it out. Okay, so let c be the denominator of na by b. Okay, maybe after writing in a reduced form. Okay. Now what happens? I mean, what can you say about the C? Okay, now you use the fundamental theorem of arithmetic and write the C as a product of Qi beta I, where Qi is prime. Okay, so this is again a plus or minus 1, that doesn't matter. And this beta I, it's this beta I belongs to natural number. Okay, not natural number union H0. No, not union 0, natural number. Yeah. Here also, this is pi prime, and alpha I belongs to natural number. Okay. So what can you say about this QI? That's the question. So once you figure that out, then you are almost done. So if you observe this QI, this Q1, let me call it as a Q1. Let's say I equal to 1 to R. Some number I can write, and here is ended. So if you write Q1, Q2, etc. to QR, the set, if you see, you can see it is a subgroup. It's a subset of P1 to Pn. Why? Because when you add it, what happens is the denominator kind of stay the same, right? But you may divide some terms of that. So if you divide, if you take this number and then divide some common factor, maybe some prime can get cancelled, but there will be no way you can add any prime. There will not be some prime cannot add there. So maybe these two primes can get cancelled. So whatever comes here, this one, these are all the same primes here. Okay. So what happens is when you do n times a plus b, whatever the prime that appears in the prime factorization, only that primes can come. Okay. Now what we know is the prime is infinite, right? There are infinitely many primes. So we say there are. So this is one of the very famous statement, one of the first statement that involves the contradiction. So we know that there are infinitely many primes. Okay, so what I can do is I can choose a prime P. Let's say capital P, which does not belongs to this set P1 to Pn. Okay, and consider that 1 by P. Okay, so what you can see is this 1 by P does not belongs to this set. Right? Because if you look at any set here, any element here, any element has, if you look at the denominator, the primes comes only from this collection. But then this prime is not inside that. So this element cannot be inside this. Okay. So that tells you there is a, so if you take any element of this, so this is a question, I'm not saying it is equal, it's a question. So suppose, let's say, that is what I'm doing. So basically what we did is we find a element here which is in Q, but it is not inside any cyclic subgroup generated by any element. So that means this Q cannot be cyclic. Okay. Is that clear? So basically what we proved is if you take any cyclic subgroup, Q is not contained in that. So that is what we proved. So Q is not equal to any cyclic subgroup. Q is a cyclic subgroup means Q is a cyclic means it is generated by some element, right? We just proved that take any element and generate, you will never get Q. Okay, that is what we did. So we have 1 by P belongs to Q, but 1 by P does not belongs to A by P. Okay. So given any A by B, you can always choose this particular P. That P depends on A by B, of course, but you can always do for any element A by B. So that tells you this Q is not cyclic. Okay, so this we have done. Let's move on to another one. Here we have another one, which says whether R is cyclic, whether C is cyclic. Maybe this one also I will do, but one can do directly, like you have to go like all this way. Similarly, you can prove here, but I will probably tell you one thing. I mean, other I can use the isomorphism directly and I can prove it, but maybe I will skip this. Okay, anyway, I will tell you later. But let's try this one. Let's try whether R is cyclic or C is cyclic. How do you prove that? I mean, of course, one can do again but then if you want to prove R is cyclic or something, you will not have this form, right? Q you can write it as A by B, but R you cannot write it as A by B. So if you want to prove R is cyclic, you cannot use any of this prime factorization, nothing you can use. So you have to come up with a different strategy. Okay, so I will tell the strategy. So the strategy is you use the fundamental theorem of cyclic group. So if you have a cyclic group, suppose let G is a G be a cyclic group, and suppose H is a subgroup of G, then what we know about H? Okay, what we know is H is also cyclic, right? Then H is also cyclic. And this is what we are going to use. So now we prove the third one. So let's say we prove R here. Suppose by contradiction, okay? Suppose, so let's go with the proof by contradiction. So suppose let's assume that R is cyclic. So if R is cyclic, what happens? Any subgroup of R is cyclic, right? So Q is a subgroup of R. Thus Q has to be cyclic. A contradiction. That's all. Because we just proved that Q is not cyclic. So since Q is not cyclic and R is some group that contains Q, R cannot be cyclic. Okay. So similarly, you can prove that C is also not cyclic. So similarly, C is also not cyclic. So yeah. So if you want to directly prove it, may be hard. I don't know. Is there a direct way? But this you can do like this. Okay. So how do you prove Q cross Q is not cyclic? So Q cross Q. How do you do? So what you can see is you can see this Q. One can see the Q as a subgroup of Q cross Q. So how do you do is you take the A here. This you kind of identify it as A comma 0. Okay. So this as a isomorphism. Okay. This identification, this goes via isomorphism. Okay. If you don't know what, if you are not familiar with isomorphism, probably you can leave this for a while until you understand isomorphism. Then you can come back. Okay. So now we know this is not cyclic. So this is not cyclic. And this is a group that contains Q, and this cannot be cyclic. So this is also not cyclic. Okay, so these are the problems we have. Now let's move on to homomorphism. Maybe I will check which are the interesting problem I have. Maybe see these are all okay. I have a few problems, but the time is less. But so I will probably do interesting one. So this is just these problems are something you just have to prove something is homomorphism. That probably you can try it. Maybe I'll leave those things as exercise. But let's do this one. So the question is find all homomorphism from Z2 to Z4. So these are interesting questions. So let's do this. Okay, so what is a homomorphism? Let me just recall what is a homomorphism. If you have map F from G to H, I call F is a homomorphism. If F of G1, it is equal to F of G1. Okay. If the map satisfies this property, then I call this as a homomorphism. So, but when I write here G, probably I have to put a dot here, which is the operation, group operation. Here, when I write here, this is the operation in G, right? And this is the operation in H. Those are different operations, not necessarily the same operation. Okay. But sometimes we just put a dot. It is understood from the context where the multiplication is happening. Okay. Okay. Now you have find all homomorphism from Z2 to Z4. So what is a Z2? Z2 has two elements, which is actually 0, 1, and Z4 has 4 elements, which is 0, 1, 2, 3. Okay. So if you have a cyclic group, if suppose you map, so first of all, what I need to do, I need to give the map this, right? So if you have a cyclic group, it is enough to map a generator. Suppose you map a generator to, let's say, some X here, some element here. That will determine the entire map. Why? Because of the property of homomorphism here. So what is, if you want to find what is f of 2, let's say, cyclic group means what? Any element, let's say G belongs to G, this G has to be written as G should be written as A power n for some n, right? So that is the property of a cyclic group. Okay, so if I look at f of A power n, then I can write it as use the homomorphism property again and again and again. You can write it as f of A power n. Okay. So as long as I know where the A maps, so basically A maps to f of A, right? As long as I know where the A maps, I know everything, where everything else maps. Okay, so let's look at where A maps here. So let's, in this case, it is additive group, so I'm using additive notation. So 1 maps to, let's say, X. Okay, so this X can be any of the 4 choices, but let's see what are the possible choices. Okay, X can be 0, right? This is possible. In that case, your homomorphism is the following. It takes, so I will probably just write here, when the case X equal to 0. So it takes 0 to 0, 1 to 0. Okay. So what about the other case where X equal to 1? So the question is whether it is possible. Okay. So if you look here, what happened? This is a group such that 1 plus 1 is actually 0. Okay. If suppose this 1 maps to 1 here, let's assume. Okay. Then what happens to f of 0, which is equal to f of 1 plus 1, which is equal to f of 1 plus f of 1, which is f of 1 is 1, right? So that is 1 plus 1, and that is 2. 2 is not equal to 0 in this group, but f of 0 will always goes to 0. That tells you 0 equal to 2, right? But that is a contradiction. So this 1 cannot be mapped to 1. That is not a possibility. So not possible. Okay. But this is equal to 0. So this is not possible. Okay, now what about this 1 maps to 2? Okay. So 1 maps to 2, is it possible? Yeah, that is possible. So x equal to 2. And what is the map here? 0 maps to 0. 1 maps to 2. Okay. Okay, and what is the other one? Other one is x equal to 3. So check, it is also not possible. Okay. Because you can see, if you, whatever you map here, what you get is 2 times that same number. If you write 3, what you get is 3 times, 2 times 3 you will get, if you map like this. Sorry, 1 maps to 3 if you map, you will get 2 times 3, which is actually equal to 2. Okay, but then it has to equal to 0. So that is not possible. So it's kind of same as this one. So how many maps you get? You get 2 maps, one here and one for here. Okay. So one map is where x equal to 0 and one other map is x equal to 2. Okay. So let's do one small more question, probably then we'll stop. This I can do, but probably we'll just do one easy one and then we can stop. Okay. So the next question, let's find all the homomorphism from Z2 to Z4. Let's say, sorry. Find all from Z2 to Z2 cross Z2. Okay. So in this case, what are the elements here? The elements are basically 0, 0, 0, 1, 1, 0, and 1, 1, right? So these are the 4 elements. So here, if you take the 1 and if you map to any of the 4 choice, you check whether that's a homomorphism. Okay. So here you can map it to any of this 4 choice, that it still gives a homomorphism. So you have basically have 4 homomorphism in this case. Okay. You have a 4 homomorphism. Okay. So what is a homomorphism? 1, let's say F1. F1, what it does is it takes 0 to 0, 0, 1 to 0, 0. What is F2? F2 takes 0 to 1, 0. Sorry, 0 to 0, 0. So F3 takes 0 to 1, 0, 0. So you got the idea, right? What I was trying to write. So that particular problem that we encountered here, this will not happen here, because you see, this has a kind of, if you take any element, if you add it twice, you will get 0. Okay. In this case, if you add it twice, it does not comes as 0. So there is a problem here. Okay. So what you do is first you write this map and then prove it is a homomorphism. Okay. So how do you prove it is a homomorphism? You have to compute this. Okay. So how many elements here you have? Here you have only 2 elements, right? So it is easy to compute. There is how many possibilities will be there? There's only 4 possibilities. If you take G and G1, there's only 4 possibilities. So you can directly write. In fact, there may not be even 4 possibilities. But anyway, you can just directly write and check that all these 4 are homomorphisms. Okay, so that will stop. This session will finish now. But later, when we do little bit more, see here you are always taking abelian group, right? Once we done the isomorphism theorems and all, we will take non-abelian groups and then we will find what are the number of homomorphism. Okay, so that later we will do. Right now we will stop. Okay, I will stop now. If you have any doubts in the lectures or something, you can ask now. Otherwise, we will meet next time.
Sir, the number of homomorphism, it is how to find out in not clear, sir. But,
Okay, you want to find the number of homomorphism, right?
yes, sir. Yes, sir. But
Okay. With the tools that currently we have, it is kind of not possible. But if you just want to do the cyclic group, if you start with the cyclic group, then you can do it. Otherwise, it's kind of not possible. If you start with the abelian group, sorry, even some other abelian group, or if non-abelian group, then it is not possible. Cyclic group, I will tell you what is the answer. You try to probably prove it. Okay. Let's say you start with a cyclic group. Yeah, that is why I take this example. So let's say you start with the Zn. I say it in more general term, okay? And you mapping it to some other group G here. Okay. So the homomorphism here, this F here, this F corresponds to element G belongs to G, such that the order of G has to divide N. Okay. So find all the G here, such that the order of G divides N. Okay. And you take this one and map it into this particular G. Okay, all of them gives a homomorphism. And you can check those are all different, because the one maps to different element, all of them are different, and you can prove it is homomorphism. But what you have to observe is the order of G has to divide N. Otherwise, you will end up with a problem like this. The same kind of problem will come up. So the number of homomorphism is basically the number of elements of G whose order divides that particular N. Is that clear? So let's say let's say you take this case, G is let's say set 8. Okay, so you want to find all the order of all the elements here, whose order divides 6. Okay, so what are the here if you look, if you calculate it, what you can get is all the orders. The only possible orders are basically these are the only possible orders here. Okay, and in these possible orders, how many of them divides this? Only 2 divides that. Okay, and you can observe that x power 4 is the only element which has order 2, because in a cyclic group you can compute each element what is the order. Okay, so this is the only element which has order 2. See, if you have more tools you can do it. For example, how I am telling these are the only order possible, that comes from Lagrange theorem. Okay, so that comes from Lagrange theorem, and most of the other thing that I can directly say comes from some other. Once you know a little bit machinery, then doing this became a little bit easy. But at this point, if you try to do, you can compute with the cyclic groups and abelian groups. Probably you can try to compute, provided at least the first element is cyclic. Then you can work a little bit and you can compute. In general, also, of course, you can keep on writing it in a brute force way. You can compute, but if you want some elegant way, right now we don't have enough machinery to do that. So once you did this Lagrange theorem and as well as the isomorphism theorems, then we can do it. Then we will have enough machinery to attack these kind of problems. So that we will do once we do all these things. Then probably I will do all those problems. Probably you put a non-abelian group. Let's say you put a symmetry groups here, and then we can do all these things. That we will do later. But with the machinery we have, only small things we can do. The hard ones we cannot do. For example, this one is obvious. If you have order 2, how many elements of a cyclic group has order 2? That we know, right? In a cyclic group, you kind of know everything. Okay, so if you have a x power a, what is the order of this? This is basically 8 here by a comma 8, right? So then you can just compute what are the order. You can see that only 4 has that order 2. So the GCD basically has to be 4. So basically a comma 8 has to be 4. And then there is only a possibility for that is basically a has to be 4. Because you are looking from 1 to 7. And then you have to get a comma 8 is 4. So this has to be 4. So those kind of these things we have the machinery right now because we know the cyclic groups. But in general attacking, if you change a group here, it's not easy at this point. One can do, but it's not easy. In fact, in general, if you put a random group here, let's say you put a large enough group here, in general it is not easy. For example, if I randomly tell you there's a group with this order, finding all the homomorphism is it's in general we don't know. So for example, if you want me to ask a question like this, suppose you gave me a size of the group, let's say you call it n, and if you ask me a question, hey, what can I say about the automorphism of G? Can you even tell the author of this? Okay, so okay, here I'm telling homomorphism, right? Then probably I will just change it to homomorphism. So basically, if you look at this one, homomorphism from G to G, from same group to same group. Okay, so when I write something like that, this means a set of all homomorphism from G to G. Okay, so this is like a G to G. You take the phi, and all the phi is here. And if you want me to find what is the order, in general, I don't know the order. So these are, of course, one can say this order is less than n power n, but exact order I don't know. Even if you gave me the group itself, still it is not easy to find just even this one. It's not easy to find. But it's not easy. But of course, you can find once if you have a group, you can compute. There are codes you can do in computer. Also, it is implemented. But in general, if you don't give the group completely, finding it's not hard. It's hard. unless you give me the group explicitly. In general, it is hard, but right now we may not have the machinery to do many of these things. Okay, but if you want, I can also give the see that group is implemented in computer also. So if you want to compute some such things, and if you want the code, probably I can give you how to use that, and all I can show you. If you are interested, I can do. Okay, maybe after the lecture you can tell me, then we can do.
Okay, so more examples to find out the number of homomorphisms.
Next class, whenever once we developed this tool, then probably we spend a lecture. Spend one class or something just to do this isomorphism theorems. Okay. Once we have the tools, then we do a lot of things, because these problems are actually interesting, and sometimes it will be little tricky also. But once you able to do it a few problems, then it will be easy. So once we have the tools, then we will do all of this.
Okay, sir. Okay, sir.
Okay.
Thank you, sir. Thank you.
Yeah. See you then. Bye.
See you, sir.
Thank you, sir.
Yeah. See you.